All right, hello everybody. We are back with the last of the n-squared sorting algorithms, at least that we're going to look at. There's a bunch of n-squared sorting algorithms because they're pretty easy to come up with, but we're only going to look at these four here. So the last one is gnome sort. So gnome sort is sort of a variation on insertion sort, but it's kind of a little bit of like a magic trick here. It's an O(n) squared time algorithm, right? But it has only one loop, not a nested loop, and one loop variable. So n squared, but no nested loop, and only one loop variable that we're using. So gnome sort is based on a simple set of sort of rules here. So there's a gnome, right, like an elf or whatever like that, wandering around in our sequence. And the gnome can move left or right one step at a time, one position at a time, and it can look at the current element, the element that it's kind of standing on, and it can look at the element to like its left or its right. It can have look at its neighboring elements, but not further than one position away there. The gnome starts at position 1. So the positions are numbered like array indices 0 through n minus 1. So position 1 is sort of like, the second position here. If the gnome ever finds itself at position n, which is 1 past the end here, stop. That means we're done. So if it ever moves all the way to the right, we're finished. If the gnome ever finds itself at position 0, it immediately takes a step to the right. So it just increments its position there. So otherwise, the gnome is somewhere between position 1 and position n minus 1 there. So the gnome is going to compare the current element to the element to its left. Now, if the current element is less than the left element, the gnome is going to swap them and take a step to the left. If the current element is greater than or equal to the left element, the gnome takes a step to the right. So those are the sort of basic rules that we have there like that. So note that this only requires one variable, right? We're just tracking the gnome's position, and we're basically running rules 4 and 5 in a loop until rule 3, which is like if we reach the position n, it triggers, and then we end the loop here. So we have one loop and one variable. All right, so let's try this out to convince ourselves that this actually works. So I put a little summary of the rules over here so that we can sort of refer to them. So we're starting at position 1, so that's why the gnome is at position 1 there like that. So we're going to compare this value to our neighbor. We're going to compare -1 to 5. Which rule triggers left? It is current less than left. That's rule 4a. So we're going to swap and move left. Now the gnome is at position 0. So that triggers rule 3. So we take a step to the right. Now we're going to compare, right? Current is greater than or equal to the left. So we're going to move to the right. We're going to compare current to our neighbor. Current is less than left, so we're going to swap and move left. Right. But now we're going to compare to our neighbor, right? And we're greater than or equal to. 4 is greater than or equal to -1, so we're going to move right. So you kind of get a feeling for how this works, right? Basically, the gnome walks right, looking for something that is out of place, like the 2 here, and then as soon as it finds it, it drags it down to the left until it reaches the correct position. So it's going to drag the 2 down until it's there, and then it's going to start walking right again. So it's going to go doot, 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 and then grab the 1, and then drag the 1 down until it reaches the correct position, and then it's going to walk right again. So it putters back its way up here, grabs the 6, which is out of position, puts it there, walk right again, grab the 5, drag it down to where it ought to be, and then walk right until we hit position 8. When we hit the last position, position n, that means the sequence is sorted. So the gnome is basically like walking to the right, looking for things that are out of order, and when it finds one, it drags it by swapping it down to the left there like that. Yeah, we're done like that. So you can translate this into code without much work. So we have a variable, g, that keeps track of the gnome's position, and rule 1 says we start at position 1. Rule 2 says we stop when we equal to n, so we're just going to make a while loop that runs as long as g is not equal to the size here. Rule 3 says if our position is ever 0, take a step to the right. So that's just incrementing g to move to the right. Rule 4a says if the current element is less than my left element, then I'm going to swap them and move left. Otherwise, I'm going to move right. So one loop, one variable. So unlike the other n-squared algorithms, it's not even obvious that like this even works, right? Like, so but before we try to analyze its like runtime, we probably might have to convince ourselves that like, yeah, that this actually even works as like an actual sorting algorithm here. So the key to this is we're going to sort of assert everything to the left of the gnome's current position is sorted. So wherever the gnome is standing, everything to the left of that position is always sorted. So if this is true all the time, and then we eventually reach position n, that means everything will be sorted. Everything to the left of the end of the array will be sorted there like that. So we just have to show that this is always true, that everything we do inside of the loop preserves this property, that everything to the left of the gnome's current position is sorted. So rule number one, right, is like, okay, start at position 1. There's only one thing to its left, and a sequence of length 1 is always sorted, right? So the assertion that we made that everything to the left of the gnome is true at the very beginning, right? When the gnome starts at position 1, the thing at position 0 is sorted. The rule about where to stop doesn't change anything, so like that doesn't sort of affect what we're talking about here like that. The rule that says if we're at position 0, move to the right. If we're at position 0, then nothing is to our left here, and an empty sequence is always sorted. So moving right puts us into the same state as the starting point there like that. So the interesting rules are 4a and 4b. We need to verify that whenever we do 4a or 4b, if everything to the left was sorted before, after everything to the left will still be sorted. So 4a is the one that says if current is less than left, we want to swap and move to the left there like that. So let's say that we have a y that is less than x here. So everything to the left of x is already sorted. That's our kind of assumption, right? Is like going into this, we have that sort of state there. We just need to show that after we do the swap and move left, it will still be already sorted here. So we swap the y down here, and then we move to the left. So if everything to the left of like this, right, was already sorted there like that, then when we move here, this stuff over here is still already sorted, right? This is just a portion of what we had before there. So everything to the left of the gnome's new position is still going to be already sorted there. So this case sort of preserves our property. It makes the part that we're sort of assuming to be sorted a little bit smaller, but it preserves that property. On the other hand, if we move right, we have to say like, well, when do we move right? So again, assume that this section here, everything to the left of the gnome is already sorted here like that, right? So when I move to the right, I'm basically going to be like adopting z into the sorted section there. So adding z to the sorted section better not break its sortedness there like that. But the only case in which the gnome moves to the right is if z is greater than or equal to y, which means that adding z to the sorted section does not break the sortedness of it, right? If we moved right without checking to see that z is greater than or equal to y, then we might add a thing that is out of order to the sorted sequence, but we don't. We only move right if y is less than or equal to z, z is greater than or equal to y. So adding z to the sorted section is a safe thing to do there like that. So that means we're expanding the sorted section in this one here. So those two things together show that like this basically always holds. Like this is always true. If it's true when we start at position 1, and then the two rules that actually like do things, rules 4a and 4b, both preserve it. So if it was true before 4a or 4b, it'll be true after that there. So no matter how many times we do the two 4 rules, they're like that, rules 4a and 4b, no matter how many times we do them, this property will still be true when we're done there like that. Now, we have a loop where we increment and decrement here. So we should probably make sure that the loop actually ends, right? Like you could write a while loop where like you increment and decrement, and it just never ends, right? Like it just sort of like gets stuck like that. So we should make sure that like we will actually reach a stopping point here. So to do this, we basically have to show that there's no pair of elements, x and y, such that the gnome could like get stuck where it's like, okay, x is here and y is here, so the gnome starts here, right? Whoops, I drew him upside down. What are you doing there, gnome? Right, the gnome starts here, right? And then he moves to the left. He or she or they, right, moves to the left, but then he or she or they immediately moves to the right. So the gnome just sort of like bounces back and forth between those two positions. I want to show that that cannot happen here. So suppose we have this setup here, right? So I have x and y. So if we know that sort of like x is going to be less than or equal to y here, that's our property that everything to the left of the gnome's position is already sorted there like that. But z is less than y. So z is out of place, so I'm going to drag z down here. So rule 4a is going to trigger, and that's going to turn this arrangement into this. We're going to swap the z and the y, so now we're over here. Now remember what we know. We know that z is less than y there. So now rule 4b is going to trigger, and we're going to move over here, right? If z is sort of greater than x, z doesn't need to be dragged any further here like that. We're going to take another step to the right here. So this is our sort of configuration. We previously swapped y and z, and now we're kind of moving to the right again there like that, right? So what do we know? We know that y is greater than z, because that's what made me do the swap, and we know that z is greater than or equal to x, because that's what enabled me to start moving to the right here. So in order to get stuck between y and z, I would need rule 4a to trigger again here. For that to happen, I would need y to be less than z. Like that would be the only case where I would drag y this way, is if y was less than z. But I already know that y is greater than z, because that's what made me put z there in the first place here. So I can't have both y less than z and y greater than z at the same time. Like that's a contradiction, right? So the gnome can't get stuck between a pair of adjacent elements there like that. That only shows it for pairs, right? You could extend that to like talk about 3 elements or 4 elements or something like that. It's a little bit of work, but basically there's no sequence of elements in our array here where we have like some stuff, right? Where the gnome will just sort of get stuck bouncing back and forth in that sort of sequence there. So we know that our loop will end, and we know that our algorithm actually sorts. So we can actually do the analysis here. The best case is if the sequence is already sorted to begin with. So in that case, the gnome just kind of wanders off to the right and then hits the sort of final position, and we're done. So we terminate after n-1 iterations there. That's the easy case. If the sequence is sorted, we just do rule 4b, 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 4b over and over until we hit position n. The worst case is if the sequence is sorted in descending order, because then I'm going to drag the 3 there, and then I'm going to drag the 2 down there, and then I'm going to drag the 1 all the way down there like that. So each new element that the gnome discovers has to be dragged all the way back down to index 0 here. So at index 1, we're going to do 1 swap, 1 decrements, and 2 increments. At index 2, we're going to do 2 swaps, 2 decrements, and 3 increments. At position k, we do k swaps, k decrements, and k plus 1 increments here. So the total work is the sum of the stuff in this right-hand column here. If we add up all that, that's the total work that we're doing there. But notice that that sum is one we've seen before, right? It's 1 plus 2 plus 3 plus 4 plus blah, 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 like that. So the total number of swaps is k times k plus 1 over 2. Total decrements is the same, and total increments is a little bit different, but they are all basically n squared when we get to position n there like that. So the worst case for gnome sort is O of n squared algorithm there. Gnome sort is basically insertion sort, right? Like the gnome is inserting things when it drags them to the left, and then the walking to the right is just to kind of figure out where we left off. Insertion sort has that outer loop with the I variable that keeps track of where we left off. Gnome sort doesn't have that, so the gnome has to walk to the right to figure out where we sort of left off in the invisible outer loop there like that. Gnome sort does more increments and decrements because the gnome does more walking around, but that doesn't change its big O's complexity. It does the same number of swaps and comparisons as insertion sort. A fun thing to maybe try would be to see if you could do a similar thing with like bubble sort or selection sort. Like, can you turn those into one loop, one variable algorithms where we're just using increments and decrements to kind of do all the work there? I'm not sure. It's kind of, I don't know, sort of interesting thing to think about there like that. Anyway, Gnome is the last, Gnome sort is the last of the n-squared sorting algorithms that we're going to sort of talk about here. So this, if you've gotten this far, is the final video for this week. And next week we will start in on the sub-quadratic sorting algorithms. That's it for now, everybody. Have a good day.